So there's one thing I forgot to mention in the last video that I want to mention here briefly before we continue. Um, is that in the last video we talked about how if we had three strain gauges with known strain, we could calculate the given state of strain epsilon xx, epsilon yy, and gamma xy um, and it can calculate the principal strains. Um, the the other thing we can do here is that with once we have epsilon xx, epsilon y, and gamma xy, we can plug them into the stress strain relationships. The one thing I want to make sure is that when you're using the stress strain relationships, make sure you're using engineering. Use the engineering strain matrix, not the epsilon elasticity matrix when you're doing those stress strain using those stress strain relationships. All right, otherwise you're gonna get the wrong answer for tau xy. Um, so just be conscious about that you know when if you're using the stress strain relationships, you need to use the engineering strain matrix. If you're using finding the principal strains, you need to be using epsilon elasticity. All right, so so the one thing that we didn't cover in last video is we solved for our three principal strains. We had epsilon AP1, we had EP2, and we had gamma max. All right, so um, so we can use these two principal strains and our maximum shear strain to actually calculate our sigma x, our sigma y, and our tau xy. All right, we just need to use the two material constants of 200 gigapascals for the Young's modulus and the Poisson's ratio of 0.3. All right, so if we plug in all of those values, all right, so what we're going to do here is we can basically to find our first principal stress, we can use this equation here. All right, so we can say that our first principal stress is going to be equal to the Young's modulus of 200 gigapascals times 1 minus 0.3 squared times epsilon x, which is going to be equal to EP1, all right, or is 360 microns, all right, plus the Poisson's ratio of 0.3 times epsilon y, which is going to be same thing as EP2, all right, which would be minus 300 microns, all right, and then so we can solve that. If we solve for all those numbers, we get 59.3 megapascals, and we can repeat the process for the second principal stress. We can use our sigma y equation here. So we'll say that that's going to be equal to the Young's modulus, 200 gigapascals, divided by 1 minus the Poisson ratio squared, times epsilon y. We're going to use EP2. All right, so we're going to say that to be minus 300 microns plus the Poisson's ratio of 0.3 times epsilon x, which was equal to 360 microns. All right, if we plug all that in, what we end up getting is we get minus 42.2 megapascals. All right, and then for the last one, or our last equation we have here, is we can solve using this equation here. We can solve for tau max. All right, and so we just have to plug in all of our values. So we just have to plug in epsilon, Young's modulus of 200 gigapascals. All right, divided by 2 times 1 plus the Poisson's ratio. All right, times gamma xy, which is gamma max being 660 microns. So if we do all that, what we end up getting is we get 50.8 megapascals. All right, so these three values for sigma 1, sigma 2, and tau max that we achieved by using the stress strain relationships and our principal strains and our maximum shear strain, those are the same values that we got using our stress matrix when we solved our stress matrix to determine our principal stresses and our maximum shear stress. So that we got the same exact answers. So if you have, I guess what I'm trying to say is if you have the principal strains, or you have the if you have the principal strains, you can convert them directly to the principal stresses, or if you have the maximum shear strain, you can use the stress-strain relationships to find the maximum shear stress for any given state of stress or strain.